This chapter 2 teaches you how to establish a delta hedge and addresses the limitations of a static delta hedge and the need to rebalance it. We now consider a 3-month, please note 3-month, at the money sterling call, whose delta can be calculated in worksheet GK2 to be approximately 0.5 or 0.503638 to be exact. Consider now a trader that has sold this call on a notional in sterling of 1 million and is concerned that the spot may rise, which would, of course, cause him losses. The trader goes ahead and purchases 503,638 sterling spot, calculated very simply as the notional of the call multiplied by its delta. We might say the trader is short the call and long the delta of the call in the sterling spot market. This top half of the slide shows the aggregate position of the trader, both initially and following a 1 cent increase and decrease in the spot rate. The key point to note here is that while each component of the trader's position changes by something close to $5,000 in value when the spot changes in either direction, up or down, the aggregate position for the trader loses only some $260 or so because the two components have moved by roughly equal and opposite amounts. Indeed, if we had simulated a movement in the spot of 0.1 cent instead of 1 full cent, as illustrated in this bottom half now of the table, we would have found the two components moving by almost exactly equal and opposite amounts, because our determination of delta would have been so precise that our hedge imprecision would be practically negligible. It should not be hard for you to understand why the hedge works so well, given the definition of delta. We know that when sterling spot rises by 1 cent, as shown on the right, the call rises in value by, and therefore generates a loss for the trader equal to notional times delta times 0.01 measured in dollars. But the trader is long an amount equal to the notional times delta units of sterling spot, and so has achieved a gain in dollars of n times delta times 0.01 in dollars again, which offsets his loss under the option. The calculation would simply be reversed for the case of a 1 cent decline in spot, with the short call generating the gain for the trader and the long sterling spot generating the loss. Now let's take the case of a trader that has sold a put option on 1 million of notional sterling. This trader would need to short sterling by the amount of the puts delta, which comes to 0.483940 according to worksheet GK2. The trader therefore shorts 483,940 sterling spot, which means basically borrowing this amount in sterling and converting it into US dollars. If now sterling changes by 1 cent up or down as before, we can see the effect on his aggregate position in this top half of the table. This time, of course, it is the short put that generates a gain for the trader when spot rises, and the short sterling position that generates the loss, and vice versa when spot falls. The bottom half of this table confirms again that if we simulate a movement in the spot of only 0.1 cent in either direction, our hedge becomes very nearly perfect as it did for the call. You can probably guess what the trader needs to do to be delta hedged if he purchases the sterling call or the sterling put. Click on pause, think this through, and then click on play when you are done thinking to hear the answer. This table summarizes how the trader creates his delta hedge for each of the 4 basic option positions. And therefore, in answer to the question we just raised, if the trader is long the call, he would short the spot, and if he is long the put, he would go long the spot. In each case, it bears repeating, the size of the spot position needs to equal the delta times the notional of the option in question. This brings us to the need to rebalance a delta hedge. Let's return to the trader who had sold the sterling call and assume that shortly after implementing this delta hedge of purchasing the appropriate amount of sterling at 150, spot rises to 151 as in one of our previous illustrations. We saw already that the value of the trader's aggregate position has barely moved in aggregate, precisely because the trader was short an amount of sterling spot exactly equal to the option's instantaneous delta. But now, assume sterling increases again, but this time to 155. Now, the aggregate value of the trader's position would have changed as shown in this table, which you can confirm in your own time. On this occasion, however, the hedge did not perform as well as before, leaving the trader with a loss in excess of $6,200. The reason is simple and is illustrated on the table that has just appeared in front of you. After sterling had increased to 151, the delta of the call had itself also increased to 0.5557, as you can see here, so that the size of the delta hedge, previously set at 503,638, became inaccurate. Specifically, the trader became under-hedged and ideally should have increased the size of his long sterling position hedge by some 52,000 pounds. This process is called rebalancing the hedge and would eliminate much of the inaccuracy as the spot rises further above 151. So when the spot reaches 152, for example, the option's delta has increased again to 0.6064, which requires another rebalancing of the hedge for an additional 50,500 pounds. And then at 1.53 spot, the delta has increased to 0.65, requiring an additional rebalancing of some 48,500 sterling, and so on and so forth. If the trader had rebalanced his sterling spot hedge continuously in this manner, the amount of slippage that we encountered a minute ago, of some 6,200 sterling in total, would have been dramatically reduced. We make the following observations about the hedge rebalancing process. First, there is no golden rule for exactly when to rebalance the delta hedge. The trader could rebalance each time spot moves by 1 cent, or by 1/4 of 1 cent, or any smaller or larger amount. The trade-off is simple and probably intuitive. The more frequent the rebalancing, the more accurate the hedge at all times, but the greater the transactional costs and operational headaches for the trader. Part of the answer to this question also depends on how fast delta changes when the spot changes. When the option is deep out of the money, the delta changes very slowly, so the trader can afford to rebalance less frequently. Note, for example, that when spot is 130, delta is 0.0022, but if spot reaches 131, delta rises only to 0.0036. Thus, the necessary amount of sterling spot rebalancing for the delta hedge would be only some 1,400 sterling, far less than in our earlier examples, and the failure to rebalance at this point would be far less painful for the trader if spot continued to rise. Note also that by not rebalancing too often, the trader would avoid the loss he would otherwise incur if spot were to fall back soon after to 130. We will return to this very important point shortly. By the same token, when the option is deep in the money, e.g. when spot is 170, delta is already at 0.9819 and increases only to 0.9836 when spot rises 1 cent, requiring therefore a rebalancing of only 1,700 sterling. So it is common to find the traders rebalancing infrequently or rarely when the option is either deep in the money or deep out of the money, but rebalancing much more frequently when the option is close to the money. We have hinted previously that the rate at which delta changes is what is known as gamma. So it seems critical for the trader to know when an option's gamma is low and when it is high. We will discuss this in detail shortly, but for now you should be aware that at the money options have more gamma than in the money or out of the money options, so would require more frequent rebalancing under the above analysis. And furthermore, if an option is close to or at the money as it approaches expiration, its gamma rises very rapidly and makes it necessary for the trader to rebalance extremely frequently. We are now in a position to tie option pricing to the delta hedging process. We have seen that by being delta hedged, the trader ensures that his P&L is essentially immunized from small subsequent movements in the spot. Let's examine, however, a case in which spot rises quickly to 151, then falls back to 150 soon after. We saw previously that when spot rises from 150 to 151, the delta increases from 0.5036 to 0.5557, requiring the trader to purchase in aggregate an additional 52,000 or so sterling. So he purchases these additional sterling, but at this new higher price of 151. When spot drops back to 150, the delta once again reverts to its initial value of 0.5036, assuming, of course, that none of the other variables have moved, as always in the discussion of factor sensitivities. So the trader must now unload, i.e. resell, the additional 52,000 or so sterling, but at the new spot price of 150. The purchase of this additional sterling amount at a price of 151 and its subsequent resale at 150 translates, in this example, into a loss for the trader of 1 cent per sterling, or $521 in total. Now consider the case in which spot starts at 150, as before, then promptly rises to 152, causing the trader to rebalance his hedge for the first time, and then promptly falls back to 150 once again. This time, the new delta when spot reaches 152, you may recall, is 0.6064, which translates into a need to purchase an additional sterling 102,789 at this new spot price of 152, and then to resell them again when the spot drops back to 150, generating a loss for the trader of approximately $2,056, or almost 4 times the previous amount. You should quickly see that these losses the trader incurs result inevitably from the very process of delta hedging a short call position. The trader must purchase sterling spot initially, and must purchase more sterling when spot rises, and must sell some of it when spot falls. Thus, he is in effect buying high and selling low, and does so more frequently when markets are choppy, i.e. volatile, than when they are relatively stable. Stated another way, his losses from rebalancing are greater when the spot is more volatile. Hence the critical role of volatility in the pricing of options. The premium the trader charges for selling the call option is principally a reflection of what in aggregate his rebalancing costs are expected to be, given some assumption the trader makes about the currency's likely volatility over the term of the option. The greater the expected volatility, the greater the frequency and the magnitude of necessary hedge rebalancing, and the more the trader must charge by way of a premium to offset those inevitable losses. Now comes the most beautiful part of the Black-Scholes theorem and its affiliates, such as Garman-Kohlhagen, GK. Subject to the assumptions of Black-Scholes, which we will go through in a second, it can be proven mathematically that a premium determined by the Black-Scholes formula will exactly offset the trader's losses on a time value adjusted basis from the delta hedging process, provided the realized volatility of the underlying currency, in this case, over the option's life turns out to be exactly equal to the expected volatility that was used as the volatility input in the formula. To make a profit, of course, the trader would pad his price above what the formula generates when he is selling options, and below what the formula generates when he is buying options. The corollary of the above principle should be easy for you to anticipate. If the realized volatility turns out to be lower than the expected volatility that was used in the formula, the trader walks away with a profit if he was short the option, and a loss if he was long the option. If the realized volatility turns out to be higher than the implied volatility used in the formula, the trader walks away with a loss if he was short the option, and a profit if he was long the option. The assumptions underlying the Black-Scholes formula are technical and tedious to understand in detail, so are left for an advanced quantitative module. But here are the principal ones. Interest rates are constant. Spot moves continuously without jumps. The trader can transact in the spot or forward market at any time, in any amount, without transaction costs or taxes, and without moving the market. Volatility is constant. The trader can go short without limitation, and very importantly, the returns of the underlying currency, or whatever asset class we're talking about, are normally distributed, i.e. the graph plotting the magnitude of returns against their frequency looks like the bell curve that we saw in the module FX options.